Hello everyone. This video we are talking about section 10.5, graphing quadratic functions, parabolas. Yes, the graph of a quadratic function is a parabola. Let's start from the definition of a quadratic function. We know what is function, right? Remember, I described a function as a machine. Whenever you give the machine an input, the machine would produce a unique corresponding output for the given input. A function could be written as an equation. So this is a function. X is the independent variable. X represents all the inputs. Y is the dependent variable. Y represents all the outputs. Y equals ax squared plus bx plus c. At this point, you should be very familiar with this trinomial. Okay, so this function is a polynomial function. Because the degree is 2, so we call this function quadratic function. Is that clear? Quadratic in algebra means degree 2. Polynomial function with degree 2. A, B, C, those are numbers, constants, real numbers. This fancy R represent a real number set. I used this notation before, but you don't have to worry about that. All this means A, B, C, they are constants, they are numbers. A is the coefficient of x squared, B is the coefficient of x, C is the constant term. And A here, the leading coefficient, must be non-zero. Think about if we have A equals 0, then we don't have this term anymore. Then the equation becomes a linear equation. And we know, if we don't have this term anymore, then we have a y equals bx plus c. That's a straight line, right? Yeah, we are talking about quadratic function. So the leading coefficient a must be non-zero constant. Any function which can be written in the form y equals ax squared plus bx plus c is a quadratic function. That's the definition. Also, from the definition, you can see this equation is the standard form. Very important because we're going to have another form later. Yeah, this equation is the standard form of a quadratic function. In the standard form of a quadratic function, left-hand side we have a y, right-hand side we have a quadratic trinomial, leading term, middle term, constant term. Okay, yeah, the focus of this section is the graph of a quadratic function. The graph of a quadratic function is a parabola. We know what is a parabola, right? This is a parabola. This is a parabola. This could be a parabola. Well, this could be a parabola, right? Or even this way. This is a parabola as well. But think about our vertical line test. Vertical line test. This graph does not pass vertical line test. So this graph could not represent a function. Same thing here. Same thing here, right? So the parabola facing to the right or facing to the left or whatever other direction, those parabolas are not going to be functions. I just showed you. They fail the vertical line test. When we talk about the graphs of quadratic functions, the parabolas either opens up like this one or opens down like this one. The parabolas must be vertical parabola, either opens up or opens down, okay? So we are clear about that. The corresponding graph of a quadratic function is a parabola, is a vertical parabola, either opens up or opens down. Then you might ask, when the graph is a parabola opens up, when the graph is a parabola opens down. depends on A. Okay, I have that in my notes. If A is positive, the leading coefficient is positive, then the graph of the quadratic function is a vertical parabola. Vertical parabola opens up or opens upward. Something like this, you see. Okay? Yeah. And if the leading coefficient is negative, then the graph of the quadratic function is a vertical parabola opens down or opens downward. W-A-R-D. It's something like the parabola is going to look like this. Okay? Yeah. I'm going to explain why. How come? I'm going to explain in a moment why the sign or the positive or negative of the leading coefficient determine how does the parabola opens up or opens down. Okay, I'll explain later. So we're gonna talk about example 1. From example 1, you're gonna see another form for quadratic function. It's called a vertex form. Example 1. Rewrite each of the quadratic function in the vertex form. Rewrite the quadratic function in the vertex form. We just talk about standard form, right? Here we have a new concept, vertex form of a quadratic function. I'll explain. And what is the vertex form for a quadratic function? It is y equals. Also, dependent variable y is on the left by itself. On the right hand side is different. A times parentheses x minus h to the power of 2 plus k. Right? So we are actually talking about the concept of a vertex form, the vertex form of a quadratic function. Vertex form of a quadratic function. X, this is a function, remember. This is still a function. X is the independent variable. Independent. See, how do we rewrite a function, quadratic function? If the quadratic function is given in the standard form. You see we have two forms, right? For quadratic function. You can see this is the standard form. The given function, the function quadratic function is given in the standard form. We need to rewrite the function in the vertex form and then identify the vertex. The purpose we want to rewrite the function in the vertex form is to identify the vertex. What's the title of this section? Graph the quadratic function, right? We know the graph is a parabola. Then when we graph the parabola, we want to know the location of the vertex. We want to know the x-coordinate, y-coordinate of the vertex. Then we can draw the parabola, right? Okay, so how do we do that? How do we rewrite the function in the vertex form? This is how. Firstly, look at the leading coefficients. In this case, the leading coefficient is 1. Then we don't have to factor the leading coefficient out. Later examples, you would see if the leading coefficient is different from 1, we would have to factor it out. In this case, the leading coefficient is 1. It's a simple case. then we do not have to factor the leading coefficient out. And we can go ahead to completing square. The constant term is -4. Obviously, this trinomial is not a perfect square trinomial. So we would have to completing square. We have to make a perfect square to happen. The way we do it is this. So do you see the two cells? The original function is x squared minus 2x minus 4, right? Yeah, between -2x and -4, I'm going to add a number and then subtract the same number. We are changing the looks. We're changing the form of the function. We are not changing the function in itself. So we're going to add a number here and then minus a number here. The two numbers must be the same to keep the function unchanged. So what number here? Coefficient of x. Okay, the number, what's the coefficient of x? Original function is a quadratic function, so the middle term coefficient of x is -2. 1. What's again? The number is gonna be the square of half of the coefficient. How many terms now we have in the first three? The first three could make a perfect square. You can try the factoring method. X squared minus 2x plus 1 would give us x minus 1 to the power of 2. Okay? Because the -1 times -1 plus -1 is -2 of number happen to be half of the coefficient of x. Half of the coefficient of x. To summarize things. And you remember those things. The next time you would know how to apply it. Again, the first three terms give us coefficient of x is -2. Number is half of the coefficient of x. Coefficient of x is -2. Apply the square of x minus 1. Okay? So far, so here we go. That's how do we apply completing square to write a function in the vertex form. You can compare. This is the formula. This is the vertex form we got for the given function. Question, what is A? What is A? What's the leading coefficient? What's the coefficient of the perfect square? It is 1, right? Yeah, leading coefficient is 1. It is positive, so the problem opens upward, opens up. And what is h comma k? The vertex is h comma k. What is h? What is k? Huh? What is h? What is k? K is easy, -5. And what is h? It is very easy to make a mistake here. Because in order for y to have the value -5, the perfect square part must be 0. In order for the perfect square part to be 0, the base inside the parentheses must be 0. In order for the base x minus 1 be 0, x has to be the opposite of -1, which is a positive 1. So I would recommend you repeat the part that I just said over and over to read it out. Be very careful. You plug in x equals -1. -1 minus 1 is -2. -2 to the power of 2 is 4. 4 minus 5. It will not give you the corresponding y value -5. Yeah, one benefit of doing the video is you can pause, watch the video, you can pause it, and can repeat that part over and over until it makes sense to you. So now we identify comma -5, the 1. We want to make the problem as accurate as possible. First one is 1 plus have this y-intercept. Yeah, make x be 0. So you have y equals -4. Thus, the y-intercept is 0, -4. I think we pretty much have all the need negative 1, -5, 1, -5. So we would have to do one more here. Vertex is right here. And we know it opens up. Yeah. Also, maybe opens up. Yeah. Also, maybe I think the axis of symmetry helps as well. You see the value of k, right? Value of k. And the value of h. And the x 9 definition of vertex form. How do we rewrite a function in the vertex form? How do we find the y-intercept for a problem? And how do we find the axis of symmetry for a problem? And how do we the leading coefficient different from 1? Different from 1. Different from 1. I'm going to show you if the leading coefficient is different from 1, how do we rewrite the function in the vertex form. But it is a good fractions anyway. Yeah. So the number we're going to have here is going to plus 81 over 16, and then minus 81 square of half of the coefficient of x. Coefficient of x is 9 over 2. Half to the second power is 81 over 16. And then we are going to group them. The first 3 terms, those 3 terms are going to give us a perfect square. All right. We rewrote the number, the value of h intercept with the vertex to factor them. The number. Okay. And what's the vertex? -3, 7. -3, 7. Okay, so we have to go up.